Hi everyone, welcome to part 3 of lecture 9, and in this lecture we will cover the moment generating functions. So this part is, or the moment generating functions is really important concept, and I will give you the detail of this one, that is why that is so important. But we can think this part, the moment generating function, as a two-part, and in the first part we will look at some moment generating function of some distribution, and in the second part I will explain why that is important. But before going to the details, let me give you a quick introduction. So far we have seen the CDF of some useful distribution, right, for the discrete and the continuous case. But the moment generating functions can be much more useful than CDF, because let me tell you, we have two random variables x and y, and we know the CDF of both. Okay, then we can calculate the expected value of it, right? The expected value of x and the expected value of y. Or let's say we don't know the CDF, but we know the expected value of that two random variables. And let's say the expected value of x and expected value of y is equal. Can we say that these two random variables is coming from the same distribution? No, we cannot say that. But in the moment generating function, if the moment generating function of two random variable is same, we can say that these two random variables is coming from the same distribution. That's why that can be more useful than the CDF. Okay, we will continue with these details in terms of importance and the useful of the moment generating function. But now let's introduce what is that. Let x be a random variable, and that can be discrete or continuous. The moment generating function is defined as the expected value of e to the tx, and x is here the random variable, and t that the value that can take, and the t can be any real number. So this is called the moment generating functions, the MGF of x, if the expectation exists on some neighborhood of the origin t is 0. So what that means, if t is 0, no matter x is, no matter the value of x, that will be 1, right? So that's why we have at least one more point, the expectation will be exist. Like for the t is 1, for t is equal, if the expectation is exist, we can say that this is a valid, the moment generating function. The expected value of the random variable e to the tx, that is the definition of the moment generating function, and we know that the m of 0 is 1. Okay, that's for sure. Well, it doesn't have to exist, because remember that we need at least one value, one t value rather than 0. The expectation on it should be exist. That's why some random variables don't have an MG field, don't have the moment generating function. So that's why it doesn't have to exist. Okay. Okay, let me give you an example for that case. Consider a discrete random variable x with the following PMF, the probability mass function, which is defined as 6 over pi squared times 1 over k squared for the values k is 1, 2, 3 until infinite. So it can take any positive discrete numbers. Otherwise, the probability will be 0. First, let's check if that's a valid one, and I'm gonna check the normalization axioms. So in this case, that's mean the sum of 6 divided by pi squared times 1 over k squared should be equal to 1, right? Now let's focus on the summation of 1 k squared, and remember that, which is equal to the pi squared divided by 6. Okay, you can check your calculus class to remember the summation of this term. So, and this term will be summation of 6 over pi squared times pi squared divided by 6. These two guys will cancel out each other, and we will left with 1. So 1 is equal to 1. That means that PMF is valid. Okay. Now, let's look at the moment generating functions of this random variable, which is the expected value of e to the tx, right? How we can calculate the expected value? Remember that, which is the summation of x times PMF for the discrete case, and the integration of x times PDF for the continuous case. Now, because that is a discrete case, we will do the summation, and the expected value of e to the tx will be equal to the summation of e to the tk times the corresponding PMF, which is given to us. Well, if k is take the infinite values, that term will explode, right? That's why that doesn't convert for any t values which is greater than 0. So that's why the moment generating function is not defined or not exist for this one, for this PMF, for that random variable. That's why we say it doesn't have to exist. Okay, we cannot say any random variables should have an MGF. That's not true. Some random variable do not have an MGF. Okay, let's calculate the moment generating function of some distribution, and let's start with the Poisson distribution. But before the calculations, please don't try to memorize all these things. Okay, that will be useless, because if you are asked something about the moment generating functions like that, what is the moment generating function of the Poisson distribution, you can just simply look at the different sources and you can find what is that. So that's why the memorizing all these things is useless. But please try to understand the way of calculation of the moment generating function, and also understand why that is important and how we can use this function. And we will focus on this part in the next part. Okay. So what was the PMF of the Poisson distribution? That is e to the minus lambda times lambda to the k divided by k factorial for the k k0, 1, 2 until infinite. Okay, so this is a discrete distribution. To calculate the moment generating function, we have to calculate the expected value of the random variable, and our random variable will be e to the tx, right? How we can calculate the expected value of something, which is simply x time PMF, and that is summation for the discrete case, and the integration of x time PDF for the continuous case. So what is our x in here? What's our random variable, which is e to the tx? So e to the tk, now the k is the values x can take, times the corresponding PMF that is given to us. So summation of this multiplication will give us the expected value of e to the tx. Okay. So this guy is not based on k, that is a constant. That's why it can go outside the summation. And this here will be something like that, e to the minus lambda times the summation of k from 0 to infinity, e to the tk times lambda to the k divided by k factorial, right? And I can rewrite this guy as e to the t lambda times lambda to the k, because the k is common power, and divided by k factorial. Let's say that is x. Okay, so this guy is equal to x to the k divided by k factorial. And remember the Maclaurin expansion, which is equal to e to the x. And in this case, in our case, the x is e to the t times lambda. That's why That's why that guy, this one, which is equal to e to the lambda times e to the t, okay? Because that is our x here. So I can just rewrite this part as e to the lambda times e to the t, and I have e to the minus lambda here. That will be multiplication of these two terms, and that is equal to e to the minus lambda times 1 minus e to the t. That is the moment generating function of the Poisson distribution. Okay, again, please do not memorize these things, but understand the way of the calculation. Okay, and remember that we have at least one t values rather than 0. The expectation should be x, right? And here that function exists in infinite t values. Okay, that's why we can say that the Poisson distribution has a valid MGF, or the MGF exists for that distribution. Okay. Now let's look at let's calculate the moment generating function for the exponential distribution. Remember that the PDF of the exponential distribution is lambda times e to the minus lambda x, and we just need to calculate the expected value of e to the tx. Okay, because that is a continuous distribution, we need to integrate the random variable times the corresponding PDF. What is the random variables? E to the tx, and what is the corresponding PDF, which is lambda times e to the minus lambda x. Okay, and let's do that. So we can rewrite this part as lambda times e to the minus lambda minus t times x, because we have common things here. And the lambda is constant, and that can go outside the integration. That will be the lambda times integration of e to the minus lambda minus t, e to the minus lambda minus t times x. Now, let's do some trick here, and let's write this guy as lambda divided by lambda minus t, integration from 0 to infinity, and lambda minus t times e to the minus lambda minus t times x. Okay, so actually I multiply the inside of the integration with minus lambda minus t, and also divided it with lambda minus t. So that's mean I didn't change the results. Okay, but why I did this? Because let's say this is lambda, okay, and this is lambda, which is the integration of the lambda times e to the minus lambda x. And what is this? Actually, this is the PDF of the exponential distribution, right? And we know that that is a valid PDF. That's why the integration of this term for all possible values equal to 1. Okay, that's why this part, this guy called, is equal to 1. Okay, please don't be confused. Just instead of lambda minus t, I say, let's say that is lambda. Okay, or here instead of lambda you can write lambda minus t. Okay, so that will not change. Or you can think lambda minus t as a new lambda. That will be the same. Because that is 1, we will left with lambda minus lambda divided by lambda minus t, and that is the moment generating function of the exponential distribution. Okay. Okay, let's continue with the gamma distribution. And to calculate the moment generating function of the gamma distribution, we have to integrate the random variable times corresponding PDF, right? And we know the random variable is e to the tx, and the corresponding PDF, we know we just calculated it in gamma distribution. Okay. Now, this guy is constant and it can go outside the integration, which is lambda to the alpha divided by gamma of alpha and integration of remaining parts. Now, let's do some trick here, and to be more clear, let's take this guy, okay, this guy. Okay, and sorry. Now, let me write this part as, which is equal to lambda to the alpha divided by gamma of alpha, the integration. And if I did something, if I multiply and divide this term with lambda minus t to the alpha, lambda minus t to the alpha, and the same thing, the x alpha to minus 1 times e to the minus lambda minus t times x and dx, okay? Now, this guy is constant and it can go outside the integration, okay? So that will be lambda to the alpha divided by gamma of alpha times lambda minus t to the alpha, and the integration of 0 to infinity. And let's write this part as lambda minus t to the alpha minus 1 times lambda minus t times x to the alpha minus 1 times e to the minus lambda minus t times x dx, okay? So actually here, this is what I exactly did, okay? Now let's do some substitution, and let's say lambda minus t times x is equal to y, and therefore dy will be lambda minus t dx. Now, instead of lambda minus t times x, we can write y, right? Okay, look at this guy, this 2. I can write this part as lambda minus t times x to the alpha minus 1, right? And what is this? This is y. So instead of this thing, I can write y, right? So that is equal to y to the alpha minus 1, okay? And e to the minus lambda minus t times x. So that is y, and that will be e to the minus y, right? Because y is lambda minus t times x, and I have a minus sign here. So that's why that part will be e to the minus y, and this guy is equal to dy. Now let's consider the new limits for the new variable y. So the limits for the x is 0 and infinite, right? If x is 0, the y will be 0. That will not change. And if x is infinite, and if t is greater than lambda, that will be minus infinite. So that will not make sense, and that will not be defined. That's why the t should be less than lambda, okay? If t is less than lambda, that will be the positive, and if x takes the infinite, y will be infinite, and that will be fine. So that's why we say if t is less than lambda, okay? And that is the limit of the variable y. So we will left with this term, this whole term. What is this? This is actually the definition of gamma of alpha, okay? Please check the corresponding slides, and you will see that the gamma of alpha is equal to integration of y to the alpha minus 1 times e to the minus y, okay? And so, I mean, you can see the x instead of y, but the pattern will be same. So that's why this term is equal to lambda to the alpha divided by gamma of alpha times lambda minus t to the alpha times gamma of alpha. So this 2 gamma of alpha will cancel out each other, and we will left with lambda to the alpha divided by lambda minus t to the alpha, and that is equal to lambda divided by lambda minus t to the alpha, for t is less than lambda, okay? So again, remember that we have at least one t values rather than 0, the expectation should be exist, and we have infinite t values for the gamma distribution, and we can safely say that that is the moment generating function of the gamma distribution, okay? Okay, let's continue with the standard normal distribution. We know the PDF of it, and to calculate the moment generating function of the standard normal distribution, we have to calculate the expected value of e to the tx, and which is the integration of e to the tx times corresponding PDF. Okay, that is the corresponding PDF, and that is the random variable. So 1 over square root of 2 pi is constant, and it can go outside the integration, and we will left with this one, okay? 1 over square root of 2 pi times integration of e to the tx times e to the minus x squared divided by 2. Again, let's do some trick, and let me take this part to a new page and to be more clear, okay? Here, let me do some trick, and let's say I can rewrite this part as the integration from minus infinity to infinity, and let's multiply this guy with e to the t squared divided by 2 and e to the minus t squared divided by 2. So these two guys can cancel out each other, so that will not change the results of this integration, and again, which is e to the tx times e to the minus x squared divided by 2, right? Okay, now let's focus on this part, okay, which is this part is actually e to the minus t squared divided by 2 plus tx minus x squared divided by 2, right? And this is actually this part is actually minus minus x minus t squared divided by 2, right? Because if I open this one, I will get this one. So that's why I can rewrite this part as the integration of minus infinity to infinity, and I have a coefficient here, which is 1 over 2 pi e to the t squared divided by 2 times e to the minus x minus t squared divided by 2. Okay, and that is constant, which is dx. That is constant, and it can go outside, and this guy will be e to the t squared divided by 2 over square root of 2 pi. And from this to this is what I exactly did, okay? What is this part? And this part is equal to the PDF of standard normal distribution, right? And we know that if we integrate the PDF of the standard normal distribution for all possible x values from minus infinity to infinity, we will get 1, right? That's why this part is 1. That means I will end up with e to the t squared divided by 2, okay? So that is the moment generating function of the standard normal distribution. Okay, let's continue with the normal distribution. So we will follow the same way, and we have to calculate the expected value of e to the tx to calculate the moment generating function of the normal distribution, okay? And which is the integration of e to the tx times corresponding PDF. And this is the PDF of the normal distribution. Okay, by substituting the x minus mu over sigma with the z, or we can say x is equal to mu plus sigma z, and therefore dx will be sigma dz, right? Let's look at the first guy. E to the tx will be e to the t times mu plus sigma z, okay, because instead of x we are writing mu plus sigma z times 1 over sigma times square root of 2 pi. I didn't touch this part, times e to the, and instead of here, instead of minus x minus mu squared divided by 2 sigma squared, and instead of this guy, I can write the z squared, which is same, and this part will be minus z squared divided by 2, okay? And I will rewrite this part as this one, and instead of dx, we can write sigma dz here. So here, this guy can be written as e to the mu times t times e to the t times sigma times z, okay? And this is constant, and it can go outside the integration. So we will left with e to the mu t times integration of this guy. Well, this guy actually same with the moment generating function of the standard normal distribution, okay, which is e to the tx times e to the minus x squared divided by 2, and this whole term divided by square root of 2 pi. Actually, we have the same thing here. Instead of t, we have the sigma t, okay? So the t will be the sigma t, okay? So what was the moment generating function of the standard normal distribution, which is equal to e to the t squared divided by 2, okay? That was e to the t squared divided by 2, but we have the sigma t, the t will be sigma t, so in our cases, that will be e to the sigma t squared divided by 2. So which is equal to e to the sigma squared times t squared divided by 2. Okay, and we have e to the mu times t here. So the moment generating function of the normal distribution will be this. Okay, this is how we can calculate the moment generating function of normal distribution. Okay, so this is end of part 3, and actually which is the part 1 of the moment generating function, and in the next part we will discover why that is important and how we can use that moment generating functions. Okay, thanks for watching.